Hi students, let us now discuss the principle of moments. Look at this picture. It is looking like a beam balance. You must have studied about the seesaw and the beam balance, is it not? The shopkeepers will be having one beam balance and there will be two pans. Suppose if you keep 1 kilogram stone, okay, on the left pan and some tomatoes on the right pan, so that they are in equilibrium, then the pivot will be the center point, okay, fulcrum or the pivot will be exactly at the geometric center in the common balance, is it not? Imagine if it is a seesaw, if two equal weight persons are sitting, okay, then the seesaw will be balanced. Like that, here an arrangement is shown. There is a horizontal wooden bar. Let us imagine this is a horizontal wooden bar. And here two loads are attached corresponding to F1 on the left side and F2 on the right side. The weight corresponding to this mass on the left hand side is F1, which is acting in the downward direction. And the weight of this mass, okay, in the downward direction is represented by F2. Suppose if F1 is equal to F2, then where should the balance point called the fulcrum be located? Yes, exactly at the geometric center if they are equal weights. But here F1 is greater than F2, therefore this plank or the wooden plank cannot be supported exactly at the geometric center, is it not? So we have to shift the pivot or the fulcrum towards the greater weight, then only it will be balanced. You should know that point first. Okay, as per this diagram, let us assume that the total system, okay, is under equilibrium. It is at rest. Okay, it is not disturbed, means it will be at rest. So this system is now in two types of equilibrium. One is translational equilibrium and the other one is rotational equilibrium. Now what are all the other forces acting? Okay, total forces acting on the system. F1 acting in the downward direction, that is negative y-axis. F2 also acting along the negative y-axis downwards. And the normal reaction, okay, N is always acting at the pivoted point. Okay, where will be the normal reaction always acting at the support point called the pivot, and it will be upwards. So there are three forces, F1, F2 and N. So for translational equilibrium, first of all, okay. So for translational equilibrium, what is the condition to be fulfilled? Let us write now. This F1, okay, F1 is acting in the downward direction. So F1 into minus J cap. Similarly, plus F2, okay, plus F2 into minus J cap is equal to N, okay, N into, that is we can take plus N into J cap. So this is the net force acting on the system. F1 and F2 are in the downward direction, so the unit vector in their direction is minus J cap and N is in the positive x-axis, therefore the unit vector is what? Plus J cap. So the resultant net force must be equal to mass into acceleration, that is equal to 0 because the system is in equilibrium, it is at rest, so its acceleration is 0. So rewriting this, I can write minus F1, okay, minus F1 minus F2 plus N is equal to 0 or N is equal to F1 plus F2. So this is the condition to be satisfied by the system for translational equilibrium. Understand? Similarly, now for rotational equilibrium, what is the condition to be satisfied? If the system has to remain in rotational equilibrium also, Now it has to satisfy the condition. The net torque, okay, net torque must be equal to 0. So in this case, what is meant by torque? It is also equal to moment of the force. The rotational effect produced by each force is called as torque. Okay, students. Now in this case, there are two strings by which two loads are suspended. Is it not? Now what will happen? What will happen if suppose I will detach? If I will detach this string, if I will take a scissors and cut this string, if I will cut this string means what will happen the next moment? Yes, due to the heavy load, due to the force F1, now the total system will rotate in the anti-clockwise direction. Okay, so this left side there is an anti-clockwise moment. There is an anti-clockwise moment. And suppose let us say that this string is intact and I will cut this string means what next will happen? Due to this weight F2, okay, the entire system will rotate on the right side. Is it not in the clockwise direction? So in this right hand side, it will rotate. Now suppose if both the strings are not at all cut, they are intact. Actually the system is under how many moments of the force, how many torques are acting on the system? There are two torques. One is in the anti-clockwise direction. That moment of the force is this force F1 multiplied by this perpendicular distance D1 from the fulcrum. So D1 is the distance of this string from the pivot or fulcrum, and D2 is the distance of this load from the pivot or fulcrum. So D1 and D2 are the perpendicular distances respectively from F1 and F2. So the magnitude of the anti-clock, okay, here this is anti-clockwise, okay, anti-clockwise moment, and the right side is what? This is a clockwise, okay, moment. So this is a clockwise moment. Now anti-clockwise moment has a magnitude of this force F1 into perpendicular distance D1. So here we will write, okay. So the anti-clockwise moment is equal to F1 into D1. So this is F1 into D1. Now you must know that by convention, by sign convention, anti-clockwise moment is taken as positive. So this is a positive, and clockwise moment. What is the magnitude of the clockwise moment? This is equal to the force F2 into perpendicular distance D2. So this is F2 into D2. By sign convention, this moment is taken as negative. Is it not? And suppose if the system is in equilibrium, then the net torque must be equal to 0. That is, now net torque, that is F1 D1 is or minus F2 D2 is equal to 0, or F1 into D1 will be equal to F2 into D2, or F1 by F2, okay, F1 by F2 is equal to D2 by D1. So this is a D2 divided by D1. So this is one of the very important steps. Similar equation we have studied in Pascal's law also. So you have to recall. Understand, children? So I have written F1 by F2 is equal to D2 by D1. Now the equation 2 also can be written in another form, okay, or F1 is equal to D2 by D1, D2 by D1 times F2. So this will be another equation number 3. So here the left hand side F1 is called as the load, and F2 is called effort. Okay, F2 is called as the effort. So this ratio D2 by D1 is called as a mechanical advantage. Mechanical advantage. Suppose if F1 is greater than F2, a very great load has to be lifted with less effort. So F1, if F1 is greater than F2, then D2 should be greater than D1, or D1 should be less than D2. So D1 should be less than D2. So what do you mean by the mechanical advantage? It is a ratio of D2 and D1. This only is called as a mechanical advantage. Suppose if you want to lift a heavy rock, this is a heavy rock, okay, this is a rock. If you want to lift it, means you will have to use a crowbar. So a long iron rod called a crowbar. So with respect to this point of support, you see here this distance is shorter and this distance is longer, is it not? So here you will put an effort, and here the load will be easily lifted. It can be easily lifted. Understand? So this expression only can be applied in this case of lifting the load. So this principle only is called as the principle of moments. The sum of the algebraic sum of the clockwise moment and the anti-clockwise moment is equal to 0. Then the system is said to be in rotational equilibrium. This is the statement of the principle of moments. I hope you must have understood well. Fine.